All right, guess what time it is? Time to go over the Physics C mechanics free response questions. But first, a word from our sponsor. World's Finest Physics. We're holding a Summer Institute July 18th through 21st in Frisco, Texas. We're going to do AP Physics 1 and C mechanics topics. So if either or both of those are interesting to you, visit findphysics.com. It's not College Board sponsored, but we do cater lunch and we have giveaways. And we can combine two subjects that the College Board won't. And we actually have good presenters too. So there you go. All right. So what do we got going on here? We got two sets because two sets are better than one, I guess. And apparently, what happened was that because the exam is only 90 minutes, people on the East Coast, like students, were texting their buddies on the West Coast, like, hey, here's what's on the free response, right? So then the College Board's like, oh, crap, we better make two sets that are almost identical to each other. That'll throw a monkey wrench into it, right? Okay, so here we go. All right, formula chart. All right, what do we got going on here? So I've often fantasized about a lab setup like this for like friction or something like that. I have like a hanging mass and some kind of a pulling. It would pull the box along. It's just in real life, the tension would change and the angle change. That'd be very difficult to measure the coefficients of friction from that. And I know what you're thinking too, right? Friendly, you fantasize about lab setups. Yeah, now you know why my marriage is on the rocks, right? Okay. So the block of mass M is pulled across a rough horizontal table by a string connected to a motor that's attached to the floor. Okay, a string passes over pulley, negligible friction that's vertically aligned with the left edge of the table is shown, whatever that means. All right, the string and pulley both have negligible mass. The pulley is the height h above the table. The motor exerts constant force tension FT on the string. And the block remains in contact with the table at all times. The block slides across the table from L to 0. The combination creates friction between the table and block with UK. It's split on all right, took an entire page to tell us that crap. Okay, there's like not even any tasks on this page. All right, on the dot below, draw and label the forces, not components, that act on the block when the block's x equals L. Okay, so let's see what's right here. You got us. Everybody put mg immediately, right? All right, that's like RSTL and an E from Wheel of Fortune, right? You just automatically get it. All right, I'm going to put a big old force tension right here. And let's see, what else do I want to do here? Oh, I'm probably going to put a force friction. Okay. There is a friction. I mean, force normal. I mean, there is a friction going here, right? Okay, all good. Looks like that's going to be good enough for me. Now, here's a reader tip. Okay. If your students have this habit of like drawing the forces like out here or whatever, the AP reader is instructed not to take that. They need to actually connect with the dot. If there's any noticeable gap between the arrow and the dot, we don't take it. Of course, you should not draw components on this, but you can draw all the components you want everywhere else. So I might put tension, what was that? Theta. That's where it's a reasonable place to put it, right? Sine theta, tension, cosine theta. Okay. Derive an expression for the angle theta that the string makes with the horizontal as a function of x. Are you for real? I mean, that's just tan theta. This isn't even physics. This is trig. So tan theta, the opposite over, I guess, x is like that. So x, I don't know, just derive. So derive means you have to start with like a basic equation. What's it say on the frickin' formula chart? Anytime you derive, you want to do something on the formula chart. All right, well, A and B, what the hell's that? I'm just going to say tan theta is h over x. So x equals h over tan theta. If they say derive, you really don't want to show only one line of work. You want to show at least two. And they say, start with something on the formula chart. All right, I need all that space for that. The College Board hates trees. Okay, derive an expression for the normal force exerted on the block by the table as a function of x. Oh my gosh, this is going to be worse than I thought it was, because I have to say this. I've got to say the up forces, force normal, and tension sine theta. That up stuff goes equal to down right there. I don't do the plus minus equals 0. This up force equal to down force is good enough for me. If you do the plus and minus equals 0, then God bless you. Okay, now let's see. M is something I'm allowed to have. Is that on my list here? All right, this is the part where I tell you I haven't actually seen these yet. Okay, I'm doing this cold, so I might be making some mistakes. I hope I don't make too many, because then you won't want to go to my session over the summer, right? You'll probably think that I'm some kind of a moron. Remember, findphysics.com. Okay, so let's see here. So the M is allowed. Fundamental constants, that'd be G. Okay, so the only thing I can't do is FT, I'm allowed FT, but I can't have theta. So I'm going to draw this triangle again, H and theta and X. And so this will be square root of X squared plus H squared, right? So I think what I'm going to do is I'm going to subtract normal equals mg minus tension sine theta. And then I'm going to normally mg minus tension, and then X over radical X squared plus H squared. Okay, I think I did it right. Okay. Derive an expression for the magnitude of the net horizontal force exerted on the block as a function of position X. Okay, well, that's going to be the tension sine thing. Wait, cosine. Isn't that cosine? Where's my diagram again? It's cosine, right? All right, so I meant to say cosine. That's what I meant to say. Cosine minus the friction force equals MA. All right, so force that helps you go minus the force that holds you back. Does that have a subscript on it? Yes, it does. So you want to make sure you get a subscript on that. Now I got to put the force normal, which is mg minus F tension X over radical X squared plus H squared equals ma. Oh, wait a minute. I'm just F net. Well, whatever, I'm not actually solving for acceleration. I thought I might be solving for acceleration, but yeah, that's sure good enough for me. Write but do not solve an integral expression. Okay, look, whoever wrote this question, you meant write but do not evaluate. Okay, solve is an equation. An expression doesn't get solved, it gets evaluated, dingus. Okay, so write but do not evaluate, schmuck. Integral expression. I did not write this question. Okay, could not be used to. They could be used to solve for the work done by the string, huh? Okay, I was about to think about the network. I was about to integrate this, but really, I think I'm going to be integrating just force tension. So we know that work is an integral force dot product dx. In this case, the work will be integral of force tension, but the dot product is going to haul out a cosine theta dx. So where's this? The cosine theta. Wait a minute. I did this wrong. This is actually H, okay? Told you I was going to get it wrong. I bet you're screaming at your screen. No, it's H over, it's not X over, you did the cosine. Okay, so, I didn't even finish up here. All right, so there you go. This is what happens when you go fast, right? I'm trying to make this video fast. You want to get back to your love life, okay, or whatever it is you're doing. So let's see. That's the X over radical X squared plus H squared. I told you. I'm doing this cold. I have not looked at this before, right? I did look at the pictures when it came off the copier machine, okay? I will admit to that, okay? But I didn't actually read any of the actual questions here. Okay, so that's cosine, that's sine. I think I did that right, okay? Let's see now. Okay, I'm going to plug in the cosine. That is X over that crap. Okay, so work equals integral force tension, which I'm allowed to have. All right, it's by the string. It's not by the net force, times X over radical X squared plus H squared dx. I should probably be switching around the colors here. I have a whole rainbow of pens here, and I'm just using purple right now for some reason. I'm going to go from, well, now I need to be careful here because this value needs to evaluate to a positive. And so because this has to evaluate to a positive, I'm actually going to go from 0 to L. I know that it starts at L and it ends at 0. I'm not entirely sure how to account for that here. Maybe the F tension direction is negative, and then the DX would be also negative. No, well, I don't know, something. It can't be negative from the dot product. Whatever. Okay, somebody in the comments tell me, if it was 0, if it was L to 0, where's the other negative come from? This has to be positive because there's an acute angle here, and I learned in AP Physics 1 that if there's an acute angle between the force and the motion, then the work is positive. I think I'm done here. Okay. The string does the string do more or less or the same amount of work on the block as the block moves from L to half or half to 0? I'm going to say it does more work when you go from 0 to half. Justify your answer. From X equals L to X equals half L, the string makes an angle with the dx vector that is closer to 0 degrees. So that means the cosine of theta is larger than when going from half to 0. And then I might like draw like a picture here. I might be like, okay, force tension and then dx is, and maybe say like small angle. And I might say like later it's like that or something really ostentatious like that. That might be like as a large angle. Okay, I haven't written outside the box yet, have I? All right, if you write outside the box, then that's bad. Okay, so the doppelganger to this appears in the set 2, and in the set 2 we have a shoe, or is that a squash? What the hell is that? Okay, a small sled. You could have fooled me. All right, slides. What is with the gap here? Okay, why do you need this anyway? Okay, don't let ADD take over. All right, I'm gonna move to just different color here. How about light blue? Okay, small sled slides across a rough horizontal table. Okay, that's gonna be important. With initial velocity v naught. Coefficient of kinetic friction to sled in the table is that. String connects the sled to the device on the ground. Okay, the device maintains constant tension Ft. In the string, by unwinding the string, the sled slides to the right. Total mass of the sled is m. The string is attached to the device at x equals 0. And a height of y. Device. Okay, yeah, well, a device. Okay. Horizontal is represented by x. We have a y. The device maintains constant tension with the string by unwinding as the string as the sled slides away. This is magic. Can I just tell you? Where are you getting a motor that exerts a constant tension force even if this angle changes? And where are you getting this from? The tension in this rope connected to this shoe or whatever it is, it's the same. Well, once again, we use an entire front page in order to not really ask the students to do anything. Okay. What the hell's going on here? All right, so we got an MG. I should probably read it before I actually do it. Okay, dot below represents sled. Forces exerted on the sled a short time after 0. A short time after 0? How short? Do I have to draw the force tension going that way? I think I do. All right, so, okay. And then you've got your force normal. It's humongous. It's got 2 down forces. Sheesh. And then it's force friction because why the hell not? Okay, let's see. I'd like to not screw this up. So let's see if I can draw a decent free body diagram with some good components. Okay. The angle is there. So the angle must be up here. That's whatever the hell that theorem is called. I don't know. Okay. I do not ever care about that theorem. I just know that it's a thing. Okay. So this is going to be a tension sine theta on this side. Force tension cosine theta on that side. Sure. Okay, now, I probably ought to draw a triangle. Okay, so I'm going the y and the x, square root of x squared plus y squared. Well, friends, have you read this problem already? Yeah, I did. It looked like this when I read it already. Okay, so I already know what's going to happen because all the tasks are going to be the same. All right, determine expression for the angle theta. Okay, so if this is the theta, then I might say that tan theta is x over y. So theta is inverse tangent of x over y. Okay, all good. Derive an expression for the normal force Fn. Noodle. Okay, so force normal's up. Oh, nope, that's an equal sign. I don't have any other up forces. And then you've got an mg down, and you've got a tension cosine going down. Let's double check that that's a cosine this time, and we're not doing something stupid. Oh, what is my list of allowed variables? I'm allowed to have mu, tension x, y, and g. Okay, so not theta. So normal is going to equal mg plus tension. Okay, let's make sure I get it right this time. Okay, that's y. Really? Yeah, I guess it is. Y over that radical. Square root of x squared plus y squared. Derive an expression for the magnitude of the horizontal net force. Okay, I can't stop myself. I have to have. So there's only... That's supposed to be a friction force. There's only friction acting. Is the force making it go already over with? So it's got backwards friction and backwards tension sine theta. Okay, yeah, backwards friction and backwards tension sine theta equals F net. I wonder if they honestly care about the signs. They probably want them to be the same sign, though, because they're the same direction. Okay, so let's see what's going on here. Okay, so the friction is a mu force normal, tension sine theta net. Okay, so I'm gonna do all like I got to do this crap I did before. Was there a subscript on it? Yes. Make sure you put the subscripts on things. Mg plus force tension was a subscript on force tension. Yeah. Okay. Okay. I'm gonna have to. I'm gonna have to face the music here. Okay, so there we go. Mu K Mg plus tension. All right, where's my triangle? Okay, I need to draw a triangle. This is my calculus teacher always said in high school, right? So I mean, actually now that I think of it, your students might not have done this. Your students might have done like they would have left it as force tension cosine of inverse tangent of x over y. I bet you they might have done that. Now, I wasn't allowed by my calculus teacher to do that because he made us actually simplify it out. So your students could have easily done like cosine here on set one would have been, I'm shuffling all my papers about, it would have been cosine of inverse tangent of h over x or something like that. Like they could have done that. I bet you that they would take that. I wasn't allowed by my calculus teacher to do that in high school. Every time you left it as something like that, he'd be like, you need to simplify. I need to draw you a triangle or something like that. And do you want me to draw you triangles? How he was insulting you every time, right? So if you ever said, do I need to draw you a triangle? He was basically asking you if you're stupid. But apparently he wasn't allowed to just ask us if we were stupid. Not that he didn't. I mean, he gave us calculus tests. He could figure it out. But there's like a don't ask, don't tell type thing on stupid. So you couldn't say, like, are you just stupid, right? So, okay, so the cosine is y over this radical x squared plus y. So you know what I'm going to do what my calculus teacher taught me, okay? Screw you if you have a problem with it. Then there's an x over radical x squared plus y squared. That's your f net. Okay, we haven't even finished problem one yet. Sweet, merciful crap. Okay, derive work done by the string. Make sure you know what's doing the work. Is it the net force or is it, anyway? Okay. So what do I want to do here? I want to do, work is some kind of integral force dx, and it's a dot product, so it's really integral force. In this case, we need to be very careful because we broke this into components. It's actually the tension sine theta component. Yeah, this is actually the sine theta component that is parallel to the dx direction, right? So this is going to be tension integral from 0 to L. Tension, the sine, where's my triangle, is still going to be x over square. So it's still the x component, right? It's just the x component takes a sine this time. And I think that's going to be it. I think I've done everything I'm supposed to do. The sled comes to rest after traveling a distance 2L. As the system slides from 0 to L, the energy dissipated by friction is whatever. As the sled slides from the energy dissipated by friction is that. Which one is greater? Where's my expression for friction force? All right, here's my expression for the friction force right here. So I'm going to start off with, I'm going to say force friction is mu k mg plus force tension y over square root of x squared plus y squared, which, decreases as x increases. So less force friction, less energy dissipated, you have less ED. I know that's what I'm always hoping for, right? So you have less ED for larger X. So the energy dissipated is going to be greater for the first part and less for the second part there. How could your students have said it? Your students might have had to say that the friction is less because there's less vertical tension pulling down to make the normal greater. So less vertical tension means less normal force, less friction, less energy dissipated. That might have been the route that they would have gone. Okay, so back to this. Okay, back to set one. We've got cart one's going to roll down, cart two. There's a motion detector right there, okay. Cart one, mass 1L, reservoir, cart two, mass 2, two is bigger than 1. Reservoir incline at time equals 0. Cart 1 is released and travels down the incline, smoothly translates horizontal section. Center of mass, cart 1 moves to the distance height. Time TC, 1 reaches the bottom of the incline, immediately collides, sticks with cart 2. Two-cart system moves constant speed V. Frictional rotational effects are negligible. During the collision, is the impulse on cart 1 from cart 2 greater or less than the same as cart 1? Okay, this is equal to, okay, that's Newton's third law. Newton's third law. Okay, I'm going to say 1 pushes 2 with the same force as 2 on 1 at the same time. You don't remember this part of Newton's third law, that the two forces act at the same time? My students think that Newton's third law is cause and effect. How can it be cause and effect when they happen at the same time? I've been in a history class. All right, so on the following axes, draw graphs, magnitude, momentum of each cart as a function of time t before and after tc. When do we let go of this shit? At time equals 0, cart 1 is released. So cart 1 is gonna like gain momentum, and then it's gonna like lose a bunch of it in the collision like that. And cart 2 is just gonna like mind his own business and then like gain. So you see, we pick up 3 momentums, and because cart 1 is lighter, he's going to go to less than half of the total momentum, and because cart 2 is heavier, he's going to have more than half. But this 1 and 2 add to that 3, so we pick up our 3 momentums, then lose most of them to cart 2. Okay, show the velocity of the 2-cart system after the collision is given by this equation. This must be important. If they ever tell me to show that something, it means I'm going to be using this later on, and it's so important what they want me to use that they don't want me to screw it up. So they're not like, derive an expression for v as a function of all this bullshit, right? No, it's actually like you need to get this right. Okay, so show that. Okay, so I'm going to be all like, well, mg height, which m is this? M1g height is going to become 1/2 m1 v squared. This is going down the hill, right? So you get a v equals square root of 2gh. Okay, I see the 2g and the h there. Now for the collision, okay? So for the collision, let's see. M1, that v equals m1 plus m2 v final. So v final is going to be m1 over m1 plus m2 all times v. So m1 over m1 plus m2 all times square root of 2gh, which is the same thing as that right there. Okay, let's switch to pink now. Okay, a group of students use the setup to perform an experiment. Measure the mass of cart 1 to be blah. Cart 2 is unknown. Students perform several trials. Cart 1 is released different height h. The students graph v as a function of radical h. Where's my straight edge? It's right here. Okay, draw a line that's the best fit to this crap. All right. I always ask my students, should 0, 0 be as data point? Yes. In this case, if the height's 0, the velocity should be 0. So you probably shouldn't force it to go through the origin, but if it looks like you're going to get equal dots above and below the line and go through the origin, then why the frick not? Okay. Use the best fit line to calculate the mass of cart 2. Okay, so this looks like a slope of 1.7. The slope is 1.7. I'm going to put like an open ring here and an open ring there to say that's where I'm calculating the slope from. I'll even write it out just in case the reader's an idiot, which is not surprising. Okay, let's see. Now, what else is the slope? Okay, so if v equals radical 2g m1 over m1 plus m2 radical h, then v over radical h is the slope, which is radical 2g m1 over m1 plus m2. So I'm going to set 1.7 equal to radical 2g m1 over m1 plus m2. So maybe I'm going to swap these. I'm going to say m1 plus m2 is equal radical 2g times m1 over 1.7. All right, so that's 0.20. That's a quarter. M to radical 19.6. Quarter over 1.7. Where's my calculator? Where did I put my calculator? I don't know where my calculator is. I had it a second ago. Here it is. Okay, so got my calculator here. I should have had my ready before I started recording. Okay, so I'm going to do square root of 19.6. I'm going to multiply by 0.25 and divide by 1. Now I got to subtract 0.25. Hope I don't get a negative. All right, mass 2. It looks like it's a big 40. All right, kilograms, put units on things. Okay, so put units on things. Is this question ever going to end? Okay, good. Let's see. After the experiment, the students use a balance to measure the mass of cart 2 and find it to be less than what was determined before. Okay, to explain this discrepancy, one of the students for the mass of cart 1 was incorrectly measured at the beginning of the experiment. The students measure the mass of cart 1 again. Should the students expect this to be greater, less? Let me look. Okay, so I've got M1 plus M2 equals radical 2G M1 over a slope. Okay, so I'm going to subtract, and now I'm going to factor it. M1 times constant minus a constant called 1. So if M2 is actually less, M1 must also be less. So M1 is less than a quarter. All right. Now, what's the set 2 version of this look like? All right. So here's a set 2 version of this. All right, is held at rest while compressing an ideal spring on amount delta x. Spring constant of spring is K. Block 2 is less massive. Okay, that's fine. Block 1 is released. Time TC, the spring is no longer compressed. And block 1 immediately collides, sticks block 2. Blocks stick together and the two blocks moves constant speed V. All right, the impulse on block 1 from the spring is that. The impulse on block 1 from block 2 is that. I think that the impulse from 2 is less and from the spring is more. So I'm going to say this. I'm going to say JS gives the block momentum to go from 0 to fast. All right. But J2 takes away momentum. So the block 1 goes from fast to slow. Now impulse is m delta v. So the delta v in the collision is less than the delta v from the spring. Okay, that's my answer, and I'm sticking to it. All right. So we're going to pick up momentum, but because the spring is not linear, because the spring exerts more force at the beginning and less force at the end, this is actually a piece of a sine graph, it turns out. It does level out here, and then during the collision, block 1 is the heavier one now, so he's going to get more than half of that momentum. Block 2 is going to get less than half of that momentum. Block 2 is just sitting there, and then it suddenly gets some momentum. All right, show it the velocity. Oh, my gosh, it's the same freaking question, except this time when the spring acts, it's not mg height, it's 1/2 k delta x squared becomes 1/2 m v1 squared. So goodbye to the halves. And then we get v1 is delta x radical k over m1. Was I supposed to put m1? Yes, I was. Okay, and then now for the collision, okay, so that's going to be m1 v1. No, I'll just call it v. V1, what freaking doesn't even matter to me. M2, call it v final. So v final again is m1 v1 over m1 plus m2. So now your v final is m1 times the square root of k over m1. M1 plus m2. And yeah, if this wanders in, he partially cancels the other one. So it's going to be a square root of k m1 over m1 plus m2. These are the same freaking question. Oh, I'm supposed to put a delta x here. I'm supposed to put a delta x here from the radical, right? That's delta x right there. All right. So let's see now. Blah, 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 blah. I don't even feel like I have to read it anymore. Once you've seen one set, you've seen them both. If you don't have any delta x, you probably shouldn't have any v. So I'm going to go ahead and force it to go to the origin. Even though it's probably a bad idea, I don't care because I don't frankly care about anything at this point in my life. Okay. I'm going to go there and I'm going to go here. So what is that? Is that like maybe 52? So double that, it's 104. So as this slope is 52 minus 0 over 0.05 minus that. Probably should be very careful because that's not actually what I meant to say. Divide by that, it's actually 10.4. Okay, well, you're gonna have a calculator. I'm gonna freaking use it. So let's see, where did my other page go? Okay, so if v is radical k m1 over m1 plus m2 delta x, then v over delta x would be the slope and that'd be radical km1 over m1 plus m2. Okay, so then I'm going to set 10.4 equal to radical. What the hell am I solving for even? We know block 1, so I'm trying to solve for block 2. Okay, I'll just say km1 over m1 plus m2. Okay, so now m1 plus m2. So that's going to be 0.5, that's m1, plus m2 is equal to the square root of k, 150, m1, 0.5 over 10.4. Okay, so here we go. I'm going to take the square root of 150 times 0.5. I'm going to divide that by 10.4, and I'm going to subtract 0.5, and I'm going to get 0.33. So M2 is 0.33 kilograms. Okay. Okay, after the experiment, the students use a balance to measure the mass of block 2, find is greater than what we thought. To explain, one of the students proposed spring constant was incorrectly measured. Okay. Okay, they measure the new spring constant. So here's what I'm going to say is I'm going to say that in this, so I'm going to say M2 is equal to square root of K M1 over slope minus M1. Okay, I'm going to say if M2 is too big, then the K is too big. The new K might be less. So new K might be less. I hope I marked that correctly. All right, we're going to take a commercial break, and we'll be right back.
Give me a break, give me a break. Break me off a piece of that applesauce. Chrysler car, football cream,
Lumber tart, Snickers bar, break
Eddie!
Claude Van Damme, hair for men, poison gas, ultra sweet.
fancy feast. Break me off a piece of that fancy feast. It's a cat food. Nailed it.
Nope.
Okay, welcome back. We're still in the middle of this stuff. We're back in time for me to say, what the hell am I even looking at? All right. Solid uniform disc, vertical stand, disc stable rotating, there's friction about axle. Pass to the center disc, mass race, okay. Rotational inertia is 1/2, sure. String magnet mass straight above the disc. Attach, point B. One end of the string is connected to unstretched ideal spring constant K, which is fixed to ground. Okay. Block mass MB. All right. Attach string right side of the disc and block until the spring has equilibrium. All right. All right. There's another one where we have to take a whole one page before we can even get to anything here. MB of the block. Okay, so basically, you just say that this down force is equal to that up force. You might want to call it a tension. I think it's really the same as the KX force. So I'm going to say mg equals kx. As mg equals k. Now, what is x? X is the same as that distance right there, which would be r times theta, wouldn't it? So it'd be k times r times theta. So the m, I should probably be calling it B. Yeah, capital B. MB equals kr theta over g. All right. At time 0, the string on the right side of the disc cut in the block falls to the ground. On the circle below, which represents the disc, draw and label the forces that act on the disc immediately after the string is cut and the block is falling to the ground. Wait a minute. Hold on a second. String on the right side is cut. You cut that. Okay, and the block falls to the ground. There's no block. And why does the spring not just pull the string over? What? Surely the string does something. It's attached. Oh, wait a minute. The string is attached to the top of the disc at point P. Oh, that's so weird. All right, that's weird stuff. All right, well, let's see here. If that's the case, then I think that there's a force tension acting tangent there. I think there's also going to be kind of an mg, and there's going to be like a force from the axis right here. Yeah, okay. That's my best answer there. Angular acceleration of the disc immediately after the string is cut. Well, I'm going to go all torque equals I alpha on this thing. Torque is going to be RF. The F is going to be K times X, which is KR theta. So that's R times R theta. It's R squared theta. Why does that not make it? Oh, because there's a K in there somewhere. There's a K in there somewhere. I was like, the units will freaking work out. Okay. So now I've got to put the K, R squared theta. The I, what was the I? There it is. All right, so 1/2 mass disc. All right, what case am I supposed to be using here? Am I supposed to be using capitals? Okay, let's see. And cancel that stuff out. Oh, there's an alpha too. Let's keep that. So 2K theta over mass of the disk. All right. I don't know. Maybe that has correct units. You tell me. This is kilograms per second squared. And that's radian. That's radian per second squared. Yeah, that's the correct units. All right. At time t1, the disk is rotated, and point P is again directly above the axle. Sketch a graph of the magnitude of the angular velocity omega of the disk as a function of time. So I think that the omega is going to increase like that. And the reason I think that is because the spring is going to exert a force that varies with its stretch. So the force is going to be a lot when it's stretched out a lot. And then when the spring is stretched less, the force is less. So there's less angular acceleration, less slope. And then the force goes to zero as the spring stops being stretched. So zero force, zero slope, right? And then I suppose that this is going to keep rotating, but the string is going to go all slack, it's going to go all limp. Probably need to get a blue pill or something like that. And so it's just going to be like that. Okay, it's not going to go up anymore, all right? I told you there's no blue pill. All right, what's going on here? The disc is adjusted on support, so the axle does not. Why do you have to do this to me? Okay, the center mass of the disc. Okay, the blocks again hung on the right side of the disc, and the spring disc blocks. I can't even say this stuff. This is figure 3 axle does not exert a torque on the disc. Okay, sure. For each force on the disc, indicate whether the magnitude of the torque about the axle increases, decreases, or stays the same relative to part B. Okay. Well, what do I want to say? I guess I want to say the string on the left produces less torque. Why? Because there's less radius of action there. The string on the right produces more. I can't fucking spell anymore. This exam is making me so stupid I can't spell. All right. More torque because it was not there before, right? Because remember, the string had been cut. All right, the string had been cut. It was not there before. And then the MG now exerts torque. It didn't before because it acted at the axis. I think I've explained them all. It just says the axle does not exert a torque on the disc. Oh, end of the exam. Okay, that's my favorite words. We still have set 2 to do here. Okay, so now instead of a disc, we have this long rod that's all pointing kind of upward like that because someone's touching it. So I don't know about you. I can understand how that can happen. Okay, so the uniform board of length L and mass M is pivot L over 4 from the left of the board. Left of the board is attached to an ideal spring, constant K to the ground. Right in the board is a student spring is a stretch of the students the board is the main sort of spring stretch. On the rectangle below, draw the forces, not components, ever. Heaven forbid we ever draw components on anything. Act on the board and springs in equilibrium, forces, blah, 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 crap. All right, well, the MG comes out of the middle. You're going to have a faxis here, force of the axis, also known as faxis. You're going to have a spring force. All right, thank you. Well, fuck, I need the whole page for this. Derive an expression for the magnitude of the spring stretches delta x when the board is in equilibrium. Express your answer in terms of K, L, M, and physical constant. This is just an equilibrium question, isn't it? So can I not just say that this is the same distance? So that's just like Kx equals mg. It is balanced torques, but that R and this R are the same R. You put an R here, they're going to cancel out anyway. All right, there's a delta X is mg over K. You could not be serious. All right, what the fuck is L? L, I don't need L because it's L over 4 and L. That's the thing that cancels. M, K, I think fundamental constant is G. Do we really need a whole page for this? Good grief. Who hates trees this much? Okay. A student pushes the board down on the right side. Okay. Stretch the spring into distance x2. The board is held a small angle. Please don't let this be simple harmonic motion. Okay. And the horizontal student then releases the board for rest. Okay. At time t equals 0, the board is released. At time t equals t1, the board first crosses the horizontal. Sketch a graph of the magnitude of the angular acceleration of the board as a function of time t from t equals 0 to t equals 1. It would be a lot. Then it would be less. No, it would be 0 when you got equilibrium. And then as you go up, I'm going to have to draw this. Okay, so you're going to have a lot of force here and a little force here from mg. So you're going to have a lot of counterclockwise torque and alpha. And then here you're going to have your equal forces. And then here you're going to have like very little spring force because the spring is almost its natural length. So you're going to have a big alpha. And then you're going to have no alpha. And then small. Is that seriously the case? Okay, so it's magnitude. So if I was going to draw this alpha versus time, I draw this because this is part of a simple harmonic motion. So the magnitude, that's my best guess. Whatever. Okay. Derive an expression of angular acceleration on the board immediately after the board is released. K, L, and delta x2. Delta x2. What is delta x2? Okay, so that's a new stretch. So I want to say that the torque, L over 4 times K times delta x2. That's this. Okay, minus. It's still L over 4, isn't it? L over 4 mg. That's going to equal I alpha. So that's the torque that's making us go counterclockwise. The torque's making us go clockwise. I'm going to divide. And the L over 4 can factor out. The I can too. K delta x2 minus mg. I mean, am I missing something here? I mean, maybe this is just so exotic that it just it's supposed to confuse the student. How many pages does the problem have? Okay, what part am I on? D? 2 blocks, 5 pages long. 2 blocks of equal mass are attached to the board, equal distance from what is shown. The board is again pushed down on the right side. How does the new angular acceleration is going to be less? Why is that? Now the blocks add to the rotational inertia, but not to the net torque since they are same mass, same distance. All right, so they don't add to the net torque. So net torque is the same. I alpha, I is greater, alpha is less, so more I, less alpha. Oh, good, it's over with. Gee, now I'm going to do electricity and magnitude.